Tonight, we're going to talk about something that most people have never heard of. But that might be the most terrifying object in the entire universe. It's not a black hole. Black holes get all the attention. They're famous. They're in movies. Everyone knows they swallow everything, even light. But there's something out there that in certain ways is far more dangerous. A magnetar. A dead star so extreme that its magnetic field alone can disrupt the atoms inside your body from halfway across the galaxy. Not by pulling you in, not by trapping you, by reaching out across thousands of light years and tearing apart the very structure of matter itself. And the worst part is, you'd never see it coming. Black holes wait for you to come to them. Magnetars attack. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that sounds dramatic, but is completely physically real. Somewhere in our galaxy right now, there is a dead star no wider than a city, spinning once every few seconds, its rotation long since slowed by the very magnetic field that makes it so dangerous, wrapped in a magnetic field so powerful that it warps the shape of atoms, distorts the fabric of empty space, and could kill you from a distance that would take light thousands of years to cross. That object is called a magnetar. And to understand why it might be more terrifying than a black hole, we first need to understand what it actually is. Because the story of a magnetar begins long before the magnetar exists. It begins with one of the most violent events the universe is capable of producing. Stars don't live forever. Every star you see in the night sky is burning through fuel, fusing lighter elements into heavier ones in its core. And one day, every single one of those stars will die. How a star dies depends almost entirely on one thing: how massive it was when it was born. Small stars, stars like our sun, die relatively gently. When the sun exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant, shed its outer layers into space, and leave behind a hot, dense remnant called a white dwarf. A white dwarf is roughly the size of Earth, but contains about the mass of the Sun. It's dense, yes, but it's not extreme by cosmic standards. It will cool slowly over trillions of years, eventually becoming a cold, dark cinder, drifting through space. That's a quiet death. A dignified ending. But not all stars get that luxury. Stars that are significantly more massive than the Sun, roughly 8 or more times its mass, die in a completely different way. These massive stars burn hotter and faster than smaller stars. They rip through their fuel supply in millions of years rather than billions. And when they run out of fuel, they don't fade quietly. They explode. To understand why, you need to know what's happening inside a massive star during the final stages of its life. A star is essentially a balancing act. Gravity is constantly trying to crush the star inward, pulling all of that mass toward the center. What prevents this collapse is the outward pressure generated by nuclear fusion in the core. Hydrogen fuses into helium, releasing energy. That energy pushes outward and holds the star up against gravity. It's a tug of war, and for most of a star's life, the two forces are in equilibrium. The star is stable. But in a massive star, when the hydrogen in the core runs out, the core contracts under gravity, heats up, and begins fusing helium into carbon and oxygen. When the helium runs out, the core contracts again, heats up further, and begins fusing carbon into neon and magnesium. This process continues, with the star fusing heavier and heavier elements in its core. Neon fuses into oxygen, oxygen fuses into silicon, and silicon fuses into iron. Each of these stages happens faster than the last. Hydrogen burning can last millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts perhaps 1,000 years. Neon burning, a few years. Oxygen burning, a few months. Silicon burning, the final stage, lasts about one single day. In that last day of the star's life, the core is furiously converting silicon into iron, packing the core with iron atoms in a desperate attempt to keep the lights on. But here's the critical problem. Iron is the end of the line. Every element lighter than iron releases energy when it fuses. That's how the star has been powering itself for millions of years. But iron is different. Fusing iron doesn't release energy. It absorbs energy. It costs more energy to fuse iron than you get out of the reaction. So when the core fills with iron, fusion stops. There's no more outward pressure. There's nothing left to push back against gravity. And gravity, which has been waiting patiently for this moment for millions of years, wins. What happens next takes less than a second. The iron core, which at this point is roughly the size of Earth, and contains about 1.5 times the mass of the Sun, collapses. Not slowly, not gradually. It collapses at speeds approaching 1/4 of the speed of light. In less than a second, the core goes from being the size of Earth to being a ball roughly 12 miles across. 12 miles? That's smaller than most cities. The density becomes almost incomprehensible. A single teaspoon of the material in this collapsed core would weigh about 4 billion tons on Earth. That's roughly the weight of every car, truck, and vehicle on the planet combined, packed into a space smaller than a sugar cube. Let me say that again because the number is important. 4 billion tons in a teaspoon. What stops the collapse from going all the way to a black hole is something called neutron degeneracy pressure. During the collapse, the core becomes so dense that protons and electrons are squeezed together, merging to form neutrons. The entire core essentially becomes a ball of neutrons packed so tightly that a quantum mechanical effect called the Pauli exclusion principle kicks in. This principle says that no two neutrons can occupy the exact same quantum state. When the neutrons are packed so tightly that they're essentially on top of each other, this principle creates an outward pressure that resists further compression. The collapse halts, and what's left behind is a neutron star. A ball of matter roughly 12 miles in diameter, containing 1.5 to about 2 times the mass of the Sun. The neutron star is born in violence. The outer layers of the dying star, which have been falling inward during the core collapse, slam into the newly formed neutron star and bounce outward in a catastrophic shockwave. This shockwave tears the star apart from the inside out, producing a supernova explosion. For a few weeks, the supernova can outshine an entire galaxy of hundreds of billions of stars. The explosion scatters the outer layers of the star across space at speeds of tens of thousands of kilometers per second, seeding the universe with heavy elements like carbon, oxygen, iron, and gold. Every atom of iron in your blood, every atom of calcium in your bones was forged in a star and scattered by a supernova explosion like this one. You are literally built from the debris of dead stars. But let's focus on what's left behind. The neutron star. This is an object unlike anything else in the known universe. It's not a planet. It's not really a star anymore, though we call it one. It's something else entirely. A ball of nuclear matter crushed to densities that exist nowhere else in nature except perhaps at the moment of the Big Bang itself. The surface gravity of a neutron star is about 200 billion times stronger than the surface gravity of Earth. If you somehow stood on the surface of a neutron star, which you can't because you'd be crushed into a thin film of atoms, you would weigh roughly 30 trillion pounds. The escape velocity, the speed you'd need to reach to leave the surface, is about 100,000 kilometers per second. That's a third of the speed of light. Just to leave the surface, light itself bends around a neutron star. Because the gravity is so intense, if you could somehow hover just above a neutron star's surface and look outward, light would curve so severely that you could see most of the far side of the star, because its gravity bends light nearly all the way around. The universe would appear to wrap around you, distorted beyond recognition. These objects rotate incredibly fast. When the massive star's core collapses from Earth-sized down to city-sized, conservation of angular momentum causes the rotation to speed up enormously. It's the same principle that makes an ice skater spin faster when they pull their arms in. Except here, the arms are being pulled in by a factor of several hundred. The core goes from rotating perhaps once every few days to rotating hundreds of times per second. Some neutron stars spin so fast that their surfaces move at a significant fraction of the speed of light. These rapidly rotating neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse. If one of those beams happens to point at Earth during each rotation, we detect a regular pulse of radiation. That's how pulsars were discovered in 1967 by Jocelyn Bell Bernal. The pulsars were so regular that the first one was jokingly designated LGM1 for Little Green Men, because the astronomers initially couldn't believe a natural object could produce such precise, clock-like signals. Now, here's where the story takes a turn. Because neutron stars are already extreme. They're already among the most exotic objects in the universe. But most neutron stars are not magnetars. Most neutron stars have magnetic fields that are, by human standards, incredibly strong, roughly 1 trillion times stronger than Earth's magnetic field. 1 trillion. That's already a number that's almost impossible to wrap your head around. Earth's magnetic field is about half a Gauss at the surface. A Gauss is the unit scientists use to measure magnetic field strength. A refrigerator magnet is about 50 Gauss. An MRI machine, the kind used in hospitals, generates a field of about 15,000 to 30,000 Gauss. The strongest sustained magnetic field ever produced in a laboratory on Earth was about 450,000 Gauss, and that required enormous amounts of energy and could only be maintained briefly. A typical neutron star has a magnetic field of about 1 trillion Gauss. That's already millions of times stronger than anything humanity has ever produced. But a magnetar makes even a regular neutron star look tame. A magnetar has a magnetic field of about 1 quadrillion Gauss. That's 1 followed by 15 zeros, about 1,000 times stronger than an ordinary neutron star, and about 1 quadrillion times stronger than a refrigerator magnet. These are the most powerful magnetic fields known to exist anywhere in the universe. Nothing else comes close, not the magnetic fields of other stars, not the fields near black holes, not anything we've ever detected or measured. Magnetars occupy a category all their own. So what makes a magnetar different from a regular neutron star? The answer lies in what happens during the first few seconds of the neutron star's life. In 1992, Two astrophysicists named Robert Duncan and Christopher Thompson proposed a theory that has since become the leading explanation for how magnetars form. It's called the dynamo mechanism, and it depends on a specific and rare set of conditions during the birth of the neutron star. When the core of a massive star collapses into a neutron star, the interior is unimaginably hot, hundreds of billions of degrees. At these temperatures, the interior of the newborn neutron star is a churning, turbulent sea of neutron-rich matter. Convection currents form enormous circulating flows of matter driven by the extreme temperature differences between the interior and the surface. Think of it like boiling water on a stove, except the pot is 12 miles wide, spinning hundreds of times per second, and the water is made of nuclear matter at temperatures that make the core of the sun look like a snowball. Now, here's the critical factor. If the neutron star is born spinning fast enough, with a rotation period of about 1 millisecond, that's one full rotation every 1,000th of a second, then the combination of that rapid rotation and those violent convection currents creates what physicists call a dynamo. The same basic principle that generates Earth's magnetic field, moving electrically conducting material, generates a magnetic field. But Earth's core is made of molten iron moving sluggishly over thousands of years. The interior of a newborn neutron star is made of super dense nuclear matter moving at enormous speeds in a core that's spinning 1,000 times per second. The dynamo effect is amplified by factors that are almost impossible to calculate precisely. In those first 10 to 30 seconds after the neutron star forms, the dynamo takes whatever magnetic field the star was born with and amplifies it by orders of magnitude. A neutron star born spinning at more ordinary speeds, perhaps 10 or 20 times per second, doesn't generate a strong enough dynamo. It ends up with a magnetic field of about 1 trillion Gauss. Impressive, but normal for a neutron star. A neutron star born spinning at a millisecond period hits the sweet spot. The dynamo amplifies the field 1,000 times beyond that, up to 1 quadrillion Gauss, and just like that, a magnetar is born. But that millisecond rotation doesn't last. The magnetar's own colossal magnetic field acts as an enormously powerful brake, dragging against the surrounding space and slowing the spin within years or decades. By the time we observe a magnetar, it's rotating slowly, typically once every 2 to 12 seconds. The fast spin did its job during the dynamo phase, amplifying the magnetic field, and then the field itself shut the spin down. What remains is a slowly turning star with the most powerful magnetic field in the known universe. This process is incredibly rare. Out of all the neutron stars that form in supernova explosions, only about 1 in 10 is thought to become a magnetar. The conditions have to be just right. The progenitor star has to be the right mass, probably between about 20 and 40 times the mass of the Sun. The collapse has to produce a neutron star spinning fast enough. The convection has to be vigorous enough. If any of these conditions aren't met, you get a normal neutron star, still extreme by any human standard, but not a magnetar. As of the most recent surveys, astronomers have confirmed the existence of only about 30 magnetars in our galaxy and the nearby Magellanic Clouds combined. 30. In a galaxy containing between 100 billion and 400 billion stars. That's how rare they are. But don't let the small number fool you. 30 confirmed magnetars doesn't mean there are only 30. Magnetars are extremely difficult to detect. They're small, only about 12 miles across. They don't shine with visible light in any significant way most of the time. And their most dramatic behavior, the flares and bursts that make them detectable, happens sporadically and unpredictably. Astronomers estimate that there could be tens of millions of dead magnetars scattered throughout the Milky Way, objects that were once active magnetars but have since cooled and quieted down. The active phase of a magnetar, the period during which it produces the terrifying flares and radiation that we'll discuss shortly, lasts only about 10,000 years. After that, the magnetic field decays. The star cools, the crust settles, and the magnetar fades into an ordinary, quiet neutron star, drifting invisibly through space. 10,000 years might sound like a long time by human standards, but on cosmic timescales, it's the blink of an eye. A magnetar's active life is a brief, violent tantrum, a cosmic scream that lasts barely an instant compared to the billions of years a neutron star will continue to exist. But during that brief active phase, a magnetar is one of the most dangerous objects in the entire universe. Now, let's pause here and establish something important because it's central to everything that follows. When most people think about dangerous objects in space, they think about black holes. Black holes are famous. They've been in movies, in books, in news headlines. Everyone knows the basic idea. A black hole is a region of space where gravity is so intense that nothing can escape, not even light. And that's true. Black holes are extraordinary objects. A stellar mass black hole, the kind formed when a very massive star dies and its core collapses past the neutron star stage, has gravity so intense that space and time themselves become distorted. At the event horizon, the boundary of the black hole, time effectively stops from the perspective of an outside observer. Anything that crosses that boundary is gone, torn apart and absorbed into the singularity at the center. Black holes are genuinely terrifying in concept. But here's the thing that most people don't think about. A black hole is passive. It sits there. It waits. If you don't go near it, it can't hurt you. A stellar mass black hole is only dangerous within a compact zone around it, a region measured in hundreds of miles. Beyond that, its gravity behaves like that of any ordinary object with the same mass. You have to approach a black hole to be in danger. If you keep your distance, it can't touch you. A magnetar is fundamentally different. A magnetar doesn't wait for you to come to it. A magnetar reaches out. Its magnetic field, its radiation, its flares, these things project outward across distances that are difficult to even think about. A magnetar can affect objects that are thousands of light years away. It can ionize atmospheres, disrupt magnetic fields, and deliver lethal doses of radiation across interstellar distances. And it does this not through gravity, but through its magnetic field and the catastrophic release of energy when that field rearranges. This is the key distinction that we're going to explore in depth. A black hole is like a pit in the ground, deadly if you fall in, harmless if you walk around it. A magnetar is like a bomb. It doesn't care how far away you are. When it goes off, the blast travels outward in every direction, and if you're within range, there's nothing you can do. The explosion doesn't wait for you to approach, it comes to you. And that range, that reach, is what makes magnetars so uniquely terrifying. Because the range of a magnetar's destructive power isn't measured in miles or thousands of miles. It's measured in light years. A single magnetar flare can deliver measurable effects across tens of thousands of light years. There is nothing else in the universe, not black holes, not supernovae, not gamma-ray bursts, that combines this kind of sustained, repeated destructive reach with the unpredictability of when and where it will strike. So we have our object, a dead star, 12 miles across, born in the violence of a supernova, rotating once every few seconds, wrapped in the strongest magnetic field in the known universe. It's rare. Only about 1 in 10 neutron stars becomes one. Its active life is short, roughly 10,000 years. But during that brief, furious existence, it is capable of things that make black holes seem almost gentle by comparison. And to understand why, we need to look closely at what that magnetic field actually does. Because a magnetic field of 1 quadrillion Gauss doesn't just attract metal. It breaks the rules of how matter behaves. It distorts the vacuum of empty space. It stores energy in quantities that defy easy description. And when that energy is released, the consequences reach across the galaxy. That's what we're going to explore next. What a magnetic field this strong actually means in physical terms, and why it makes a magnetar not just powerful, but genuinely physically hostile in ways that nothing else in the universe can match. To understand why magnetars are so terrifying, you can't just know that their magnetic fields are strong. You have to understand what strong actually means at this level. Because a magnetic field of 1 quadrillion Gauss isn't just a bigger version of the magnets you've encountered in everyday life. It's something qualitatively different. It's a field so intense that it changes the fundamental behavior of matter, energy, and even empty space itself. The rules that govern everything you've ever touched, seen, or experienced simply stop working the way you expect them to. And that's not an exaggeration. That's physics. So let's build up to it. Let's start with magnetic fields, and work our way up, step by step, until we reach the magnetar. Because each step on this ladder is going to shock you, and by the time we get to the top, you'll understand why physicists use words like terrifying and impossible when they talk about these objects. The Earth has a magnetic field. You probably learned about this in school. It's the reason compasses work. A compass needle aligns itself with Earth's magnetic field, pointing roughly toward the magnetic North Pole. Earth's magnetic field is generated deep inside the planet, in the outer core, where liquid iron circulates in convection currents. The movement of this electrically conducting fluid generates a magnetic field through the same basic dynamo principle we discussed with neutron stars, though at an incomparably weaker scale. At the surface of the Earth, this magnetic field measures about half a Gauss. That's the baseline. Half a Gauss. You're sitting in a magnetic field of about half a Gauss right now. You can't feel it. It has no perceptible effect on your body, your clothes, the chair you're sitting in, or anything around you. The only thing it does at this strength is nudge a tiny magnetized needle in a compass. That's it. A refrigerator magnet, the kind you use to hold a note to your fridge, generates a field of about 50 Gauss at its surface. That's 100 times stronger than Earth's field. You can feel the pull of a fridge magnet. If you hold 2 of them close together, you feel them snap together or push apart. 50 Gauss is enough to hold a piece of paper against a metal surface. That's the extent of its power. It's a toy, a novelty, something you don't think twice about. Now let's jump up. An MRI machine, the kind hospitals use to image the inside of your body, generates a field of about 15,000 to 30,000 Gauss. That's roughly 1.5 to 3 Tesla, which is another unit for measuring magnetic fields. 1 Tesla equals 10,000 Gauss. At this field strength, things start getting serious. Before you go into an MRI, Medical staff make you remove every piece of metal from your body. Jewelry, belt buckles, hair clips, everything. Because at 15,000 Gauss, loose metal objects become projectiles. There have been cases where oxygen tanks left in MRI rooms were ripped across the room by the magnetic field and slammed into the machine at lethal speeds. People with certain metal implants can't go near an MRI because the field would rip the implant out of their body. This is 15,000 Gauss. Already dangerous, already capable of turning everyday metal objects into weapons. But compared to what's coming, this is nothing. The strongest sustained magnetic field ever produced in a laboratory on Earth was about 450,000 Gauss, or 45 Tesla. This was achieved at the National High Magnetic Field Laboratory in Florida, using specialized electromagnets cooled with liquid helium. At this field strength, you can do extraordinary things. You can levitate a living frog. The field is so strong that it interacts with the water molecules in the frog's body, creating a small repulsive force that counteracts gravity. The frog floats in midair, confused but unharmed. It's a famous experiment and a vivid demonstration of what strong magnetic fields can do. But these laboratory fields can only be sustained in small volumes, a space of perhaps a few cubic centimeters, and they require enormous amounts of energy and infrastructure to maintain. They represent the absolute limit of what human technology can produce. 450,000 Gauss, that's our ceiling. But there are brief, pulsed magnetic fields that go higher. Using explosive compression, where a magnetic field is squeezed into a smaller and smaller space by a controlled explosion, scientists have briefly produced fields of about 25 million Gauss. These fields last for only a few microseconds before the equipment destroys itself. The magnetic field literally tears the apparatus apart. At 25 million Gauss, the field interacts strongly with the electronic structure of atoms. Electron orbits are distorted. The energy levels inside atoms shift. This is useful for certain physics experiments, but the fields are so brief and the equipment destruction is so complete that these are one-shot experiments. You build it, fire it, and then clean up the wreckage. Now let's leave Earth behind entirely. A typical neutron star, the ordinary variety formed in a supernova, has a magnetic field at its surface of about 1 trillion Gauss. 1 trillion. That's 1 followed by 12 zeros. It's about 40,000 times stronger than the strongest pulsed field ever produced on Earth, and about 2 million times stronger than the strongest sustained field. At 1 trillion Gauss, you have entered a regime where everyday physics starts to break down. At this field strength, atoms are no longer the round, roughly spherical shapes you learned about in chemistry class. The magnetic field is so powerful that it exerts a force on the electrons orbiting the atomic nucleus that overwhelms the electrical force holding the atom together in its normal shape. The electrons can no longer orbit freely in all 3 dimensions. They become confined, forced to move along the direction of the magnetic field. The atom gets squeezed. It goes from being roughly spherical to being elongated, stretched out along the field lines like a tiny cylinder. Imagine taking a round balloon and squeezing it so that it becomes a long, thin tube. That's what a trillion Gauss magnetic field does to an atom. This has profound consequences. Chemistry, the way atoms bond together to form molecules, depends entirely on the shapes of electron orbits. When those orbits are distorted by a magnetic field, the rules of chemistry change. Molecules that are stable under normal conditions might not form at all. new molecular configurations that don't exist anywhere on Earth might become possible. The chemistry of a neutron star's surface, if you can even call it chemistry, is alien. It follows rules that don't apply anywhere else in the universe except in these extreme magnetic environments. But here's the thing. A neutron star's magnetic field of 1 trillion Gauss, as extraordinary as it is still 1,000 times weaker than a magnetar's field. A magnetar cranks everything up by another 3 orders of magnitude. A magnetar's magnetic field is about 1 quadrillion Gauss, 1 followed by 15 zeros, 1,000 trillion, 1 million billion. No matter how you write it, the number is staggering. At 1 quadrillion Gauss, the distortion of atoms goes far beyond what happens on an ordinary neutron star. Atoms aren't just elongated, they're crushed into needle-thin structures, hundreds of times longer than they are wide. The electron orbits don't just get distorted, they get confined to the lowest possible energy state in the direction perpendicular to the magnetic field. Physicists call this Landau quantization. In normal conditions, electrons can move freely in all 3 dimensions. In a magnetic field this strong, 2 of those 3 dimensions are essentially frozen. The electrons can only move along the direction of the magnetic field, confined to the ground state in the other 2 directions. This is not a subtle effect. It fundamentally changes what matter is and how it behaves. At the surface of a magnetar, you wouldn't find the kind of matter you're familiar with. You wouldn't find atoms as you know them. You wouldn't find molecules. You wouldn't find anything that resembles the chemistry that governs life on Earth. Instead, you'd find matter organized into structures that have no equivalent anywhere else. Long thread-like chains of nuclei surrounded by cylindrically confined electrons, all oriented along the magnetic field lines. Some physicists have described this as magnetic condensation, a phase of matter that exists only in magnetic fields above about 100 trillion Gauss. It doesn't exist on Earth, it doesn't exist in laboratories, it doesn't exist on ordinary neutron stars, it exists only on magnetars. And this is just what happens to ordinary atoms. What happens to the vacuum of space is even stranger. This is where things get truly mind-bending. You probably think of empty space, the vacuum, as being nothing. No matter, no energy, just emptiness. But according to quantum mechanics, the vacuum isn't really empty. It's a seething foam of virtual particle pairs, particles and antiparticles that pop into existence for an impossibly brief moment, and then annihilate each other, disappearing back into nothingness. Under normal conditions, these virtual particles have no observable effect. They exist for such a short time and in such a balanced way that the vacuum appears perfectly empty and uniform. But in an extremely strong magnetic field, the vacuum stops being uniform. The magnetic field interacts with these virtual particles, specifically with virtual electron-positron pairs, and affects how they behave. This changes the properties of the vacuum itself. In a magnetar's field, the vacuum becomes what physicists call birefringent. This is a term borrowed from optics. Certain crystals on Earth, like calcite, are birefringent. When light passes through a birefringent crystal, it gets split into 2 rays that travel at slightly different speeds depending on their polarization. If you put a piece of calcite on top of a piece of text, you see double, 2 copies of the text, slightly offset from each other. That's birefringence. A magnetar's magnetic field does the same thing to empty space. Light passing through the vacuum near a magnetar gets split based on its polarization. Photons polarized parallel to the magnetic field travel at a slightly different speed than photons polarized perpendicular to it. The vacuum near a magnetar acts like a crystal. Empty space itself becomes an optical medium with measurable physical properties. This effect is called vacuum birefringence, and it was predicted by the theory of quantum electrodynamics, or QED, in the 1930s. But for decades, it was considered a purely theoretical curiosity because the magnetic fields required to observe it were thought to be unachievable. Then we discovered magnetars. In 2017, astronomers using the Very Large Telescope in Chile reported evidence of vacuum birefringence in observations of a neutron star with an extremely strong magnetic field. The light coming from the neutron star showed signs of polarization effects consistent with the vacuum itself acting as a birefringent medium. This was potentially the first observational evidence that empty space can behave like a material substance when subjected to strong enough magnetic fields. Magnetars don't just affect matter, they affect the very fabric of reality. There's a theoretical limit in QED called the Schwinger limit. This is the magnetic field strength at which the energy stored in the field becomes strong enough to spontaneously create real electron-positron pairs out of the vacuum. Below this limit, the virtual particles in the vacuum exist only fleetingly, popping in and out of existence. At the Schwinger limit, the field provides enough energy that virtual particles become real, permanent particles. The vacuum literally starts producing matter. The Schwinger limit is about 4.4 times 10 to the 13th Gauss, or about 44 trillion Gauss. A magnetar's field at 1 quadrillion Gauss exceeds the Schwinger limit by a factor of more than 20. This means that near the surface of a magnetar, the vacuum is unstable. The magnetic field is literally strong enough to rip particles out of empty space. The nothingness around a magnetar isn't nothing. It's a churning sea of particles being spontaneously generated by the magnetic field itself. This is not science fiction. This is the prediction of one of the most precisely tested theories in all of physics. QED has been verified to extraordinary precision, matching experiments to more than 10 decimal places. When QED says the vacuum breaks down above the Schwinger limit, there is every reason to believe it. So what would all of this actually look like? If you could somehow survive the radiation and the gravitational forces and position yourself at a safe distance from a magnetar, close enough to see it but far enough not to be destroyed, what would you see? The answer is nothing like anything you've ever experienced. A magnetar is small, only about 12 miles across, so at any significant distance it would appear as a point of light, if it appeared at all. Most of the radiation it emits is in X-rays, wavelengths your eyes can't detect. In visible light, the surface would appear dim or even dark, but the space around it would be wrong. The extreme gravity bends light from background stars, smearing them into arcs and streaks, warping the star field behind the magnetar into a funhouse mirror version of reality. Stars that should be hidden behind the magnetar would be visible, their light bent around it, displaced from their true positions. And layered on top of that gravitational distortion would be something even stranger. The vacuum birefringence. Every beam of light passing through the magnetar's field would be split into two components, each polarized differently, each traveling at a slightly different speed. The result is that the space around the magnetar would shimmer, not like heat haze over a desert road, which is caused by air density changes, but something more fundamental. The shimmer would be the vacuum itself behaving like a crystal, splitting light at the most basic level. If you could somehow photograph this scene, you'd see a dark sphere surrounded by a halo of doubled, distorted light, with background stars smeared into ghostly arcs, each arc faintly split into two. It would be hauntingly beautiful. It would also be one of the most dangerous places in the known universe, because all of that visual strangeness is just the quiet, resting state of the Magnetars field. The beauty is a warning. What the field does to light, it does far more violently to matter and energy when the crust cracks. Now, let's talk about energy. Because the magnetic field of a magnetar isn't just a curiosity. It's a reservoir of energy so vast that when it releases even a tiny fraction of that energy, the results are catastrophic. A magnetic field stores energy. This is true of all magnetic fields, from the feeble field of a refrigerator magnet to the intense field of an MRI machine. The energy stored in a magnetic field is proportional to the square of the field strength. This means that if you double the field strength, you quadruple the stored energy. If you increase the field by a factor of 1,000, the stored energy increases by a factor of 1,000,000. A magnetar's field is about 1,000 times stronger than a typical neutron star's field. That means it stores about 1,000,000 times more energy. And a typical neutron star's field already stores an enormous amount of energy. The total magnetic energy stored in a magnetar's field is estimated to be about 10 to the 47th ergs. That's a number that means nothing in everyday terms, so let me convert it to something more relatable. 10 to the 47th ergs is roughly equivalent to the total energy output of the sun over about 1 million years. Think about that. The sun, our sun, the star that powers all life on Earth, would need to burn for 1 million years to produce the amount of energy that's sitting right now, coiled and ready in the magnetic field of one dead star 12 miles across. 1 million years of sunlight stored in an object you could drive across in 20 minutes on a highway. All of that energy packed into an object 12 miles across. This is what makes a magnetar a ticking bomb. The energy is there. It's stored in the magnetic field, threaded through the crust and interior of the neutron star, wound tightly like a coiled spring compressed to its absolute limit. And unlike a spring, which releases its energy smoothly when you let go, a magnetar's magnetic field releases its energy violently, catastrophically, and without warning. The key to understanding how this energy gets released lies in the crust of the magnetar. A neutron star has a crust. It's not like the rocky crust of the Earth. It's a crystalline lattice of atomic nuclei, primarily iron, arranged in a rigid structure and held together by the strong nuclear force and electromagnetic interactions. This crust is incredibly strong, about 10 billion times stronger than steel. It's the strongest material in the known universe. Nothing on Earth even comes close. But even this extraordinarily strong crust has its limits, and the magnetic field inside a magnetar is constantly pushing against those limits. Here's what happens. The magnetic field of a magnetar isn't static. It evolves over time. The field lines, which thread through the interior of the neutron star and extend out through the crust into the surrounding space, are under enormous tension. Think of them like rubber bands stretched to their breaking point. As the interior of the magnetar cools and the magnetic field slowly rearranges itself, stress builds up in the crust. The magnetic field is trying to move, trying to find a lower energy configuration, but the rigid crust resists. The crust holds the field in place, absorbing the stress, deforming slightly, bending but not breaking. This goes on for weeks, months, years, sometimes decades. The stress accumulates, the crust flexes, the tension builds, and then suddenly the crust cracks. When the crust of a magnetar fractures, the stored magnetic energy is released in a sudden, violent event. Physicists call this a starquake. It's analogous to an earthquake, but on a neutron star, and the energies involved are incomprehensibly larger. When the San Andreas fault slips and produces a major earthquake on Earth, the energy released is about 10 to the 25th ergs. A starquake on a magnetar can release 10 to the 46th ergs. That's roughly 1 billion trillion times more energy than the most powerful earthquake in Earth's history. All of it released in a fraction of a second, from an object the size of a city. The energy release takes several forms. Some of it goes into seismic waves that propagate through the neutron star itself, causing the entire star to vibrate like a struck bell. Some of it goes into heating the surface, producing a burst of X-rays. But the most dramatic and dangerous form of energy release comes when the fracture allows the magnetic field lines to suddenly rearrange. When the field lines snap into a new configuration, they launch enormous bursts of radiation and magnetically confine plasma into space. These are the bursts and flares that make magnetars detectable across the galaxy. There are different scales of these events. The smallest are called short bursts. They last for a fraction of a second and release energies comparable to what the sun produces in a year or so. These happen relatively frequently, sometimes dozens of times in a short period when a magnetar is in an active phase. They're violent by any normal standard, but for a magnetar, they're minor events. Pops and cracks as the crust adjusts to the relentless pressure of the magnetic field. Then, there are intermediate flares. These are larger, releasing energies equivalent to what the sun produces in thousands of years, packed into a burst lasting perhaps a second. These are rarer but still observed multiple times from the more active magnetars. And then there are the giant flares. These are the events that make magnetars truly terrifying. A giant flare occurs when a massive section of the magnetar's crust fractures simultaneously, releasing a catastrophic amount of stored magnetic energy in a single, blinding flash. A giant flare can release more energy in 1/10 of a second than the sun produces in tens of thousands of years. The radiation from a giant flare doesn't just travel into the immediate neighborhood of the magnetar. It travels across the galaxy. It crosses thousands of light years of space, and still arrives with enough energy to produce measurable physical effects on anything in its path. And this is the crucial difference between a magnetar and a black hole. A black hole's danger zone is measured in kilometers. You have to approach it to be destroyed. A magnetar's danger zone during a giant flare is measured in light years. Tens of thousands of light years. The destruction comes to you. It crosses interstellar space at the speed of light, arriving without warning, carrying enough energy to damage the atmosphere of a planet orbiting a star on the other side of the galaxy. But the energy storage goes even deeper than the crust. Theoretical work suggests that much of a magnetar's magnetic energy is stored not in the external field, not in the space around the star, but deep in the interior, in the superfluid neutron core. The core of a neutron star is thought to be a superfluid, a state of matter where neutrons flow without friction. This superfluid can carry magnetic field lines, trapping them inside the star. As the core cools over thousands of years, the interaction between the superfluid interior and the rigid crystalline crust creates complex stress patterns. The interior field pushes on the crust from below. The external field pulls on it from above. The crust is caught between these forces, constantly under strain, constantly being pushed toward failure. Some models suggest that the total energy stored in the interior field might be even larger than what we infer from the external field alone. The external field, the one we can measure from a distance, might be only a fraction of the total magnetic energy contained within the magnetar. If that's true, then the energy available for flares and bursts is even greater than current estimates suggest. The magnetar might be even more dangerous than we already think it is. This is what makes a magnetar unique among all objects in the universe. It's not just that it has the strongest magnetic field known to exist, it's that this field is a dynamic, unstable reservoir of colossal energy threaded through a crystalline crust that is constantly being pushed to its breaking point. The field distorts atoms into shapes that don't exist anywhere else. It tears particles out of empty space. It makes the vacuum of nothingness behave like a solid crystal. And it stores, in an object no wider than a city, more energy than the sun will produce in 1,000,000 years. The magnetar sits there quietly in the dark between the stars. A dead star. A remnant. A leftover from a supernova explosion that happened thousands of years ago. And inside its crust, the tension builds. The magnetic field coils tighter. The stress accumulates. The crust flexes, holds, resists. And then, without any warning that any telescope or instrument could detect in advance, the crust cracks. And when it does, the magnetar screams. Not with sound, obviously. There's no air and space to carry sound. It screams with light, with X-rays, with gamma rays, with radiation so intense that it can compress the magnetic bubble surrounding an entire planet from tens of thousands of light years away. That's what we're going to talk about next. What happens when a magnetar erupts? Because the physics of the magnetic field, as extraordinary as it is just the setup. The real horror is what happens when all that stored energy is suddenly, violently released. And one specific event, on a specific date, showed us exactly how dangerous these objects really are. On December 27th, 2004, something happened that changed how astrophysicists think about danger in the universe. It happened without warning. No telescope predicted it. No instrument saw it coming. At precisely 21 hours, 30 minutes, and 26 seconds universal time, a wall of radiation slammed into Earth's upper atmosphere with enough energy to produce measurable physical effects on the planet. Satellites across the solar system registered the blast. Instruments that had been quietly recording background radiation for years suddenly went off the charts, their detectors overwhelmed, saturated, blinded by a flood of gamma rays and X-rays arriving all at once. And the source of this radiation wasn't nearby. It wasn't in our solar system. It wasn't even close to our solar system. The source was a magnetar called SGR 1806-20, located roughly 50,000 light years away, on the other side of the Milky Way galaxy. From a distance so vast that light itself needed 50,000 years to cross it, a single object, 12 miles wide, reached out and touched our planet. But before we talk about that specific event, we need to understand what's actually happening when a magnetar erupts. Because the December 2004 event wasn't random. It was the result of a physical process that had been building for years, decades, perhaps centuries, deep inside the Magnetars crust. And to understand that process, we need to look at the 3 different scales of magnetar eruptions, from the smallest pops to the most catastrophic releases of energy the universe can produce outside of the Big Bang itself. The smallest events are called short bursts. These happen when a small section of the magnetar's crust shifts or fractures under the relentless pressure of the internal magnetic field. Think of it like cracking your knuckles. There's a buildup of tension, a sudden release, and then it's over. A short burst from a magnetar typically lasts less than a second, often just a few hundredths of a second. The energy released in a single short burst is roughly equivalent to the total energy the sun produces in an entire year. Let me be clear about what that means. The sun is a massive nuclear furnace, roughly 860,000 miles in diameter, converting 600 million tons of hydrogen into helium every single second. Every second, the sun releases about 3.8 times 10 to the 33 ergs of energy. Multiply that by every second in a year, roughly 31.5 million seconds, and you get the sun's colossal annual output. A short burst from a magnetar, an event so minor that magnetar researchers barely pay attention to it, releases that much energy in a fraction of a second. These short bursts can come in clusters. When a magnetar enters an active phase, it can produce dozens or even hundreds of short bursts over a period of weeks or months. The crust is adjusting, cracking in multiple places, releasing tension bit by bit. Each individual burst is brief and, by magnetar standards, small, but each one represents more energy than the sun dumps into space over an entire year, compressed into a flash shorter than a heartbeat. The next level up is the intermediate flare. These occur when a larger section of crust fractures, or when multiple fractures happen nearly simultaneously, allowing a more substantial rearrangement of the magnetic field. Intermediate flares last a bit longer, typically a few tenths of a second to a few seconds, and release energy is roughly equivalent to what the sun produces in 1,000 to 10,000 years. These events are rarer than short bursts, but still observed regularly from the more active magnetars. During an intermediate flare, a single dead star 12 miles across briefly outshines tens of thousands of suns. That's already an extraordinary amount of energy packed into a fraction of a second from an object the size of a city. But the truly terrifying events, the ones that reach across the galaxy and affect planets orbiting distant stars, are the giant flares. Giant flares are exceedingly rare. In the entire history of modern astronomy, covering roughly the last 60 years of space-based observation, only 3 confirmed giant flares have been detected from magnetars in or near our galaxy. 3 in 60 years. That gives you a sense of how unusual these events are. But when they happen, the consequences are staggering. The first giant flare ever recorded came from a magnetar called SGR 0526-66, located in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way about 160,000 light-years from Earth. On March 5th, 1979, instruments aboard multiple spacecraft detected an intense burst of gamma radiation arriving from the direction of the Large Magellanic Cloud. The burst was so powerful that it saturated the detectors on every satellite that recorded it. Scientists initially had no idea what could produce such an intense burst of radiation from such an enormous distance. The event lasted only a fraction of a second at peak intensity, followed by a decaying tail of radiation that pulsated with a period of about 8 seconds, consistent with the rotation of a neutron star. This was the first direct evidence that magnetars could produce flares of this magnitude, though the term magnetar wouldn't be coined for another 13 years. The energy released in the initial spike of the March 1979 event was estimated at roughly 10 to the 44th ergs. That's about as much energy as the Sun produces in 1,000 years, released in less than a second. The second giant flare came from SGR 1900 plus 14 on August 27, 1998. This magnetar is located about 20,000 light-years from Earth, within our own galaxy. The flare was intense enough to ionize a portion of Earth's upper atmosphere, the ionosphere, from 20,000 light-years away. Ionization means the radiation was energetic enough to strip electrons from atoms and molecules in the atmosphere. This is the same process that happens locally when you get an X-ray at a doctor's office, except this was caused by a star on the other side of the galaxy. The ionospheric disturbance was measurable. Instruments on the ground detected changes in how radio waves propagated through the atmosphere, because ionized gas affects radio transmission differently than neutral gas. A dead star 20,000 light-years away was altering the electrical properties of Earth's atmosphere. And yet, this event was relatively modest compared to what came next. The December 27th, 2004 event from SGR 1806-20 was the most powerful giant flare ever recorded. And it wasn't just the most powerful by a small margin. It was in a class by itself. The initial spike of the flare lasted approximately 0.2 of a second. In that 0.2 of a second, the magnetar released an estimated 10 to the 46th ergs of energy in the form of gamma rays and hard X-rays. Let me put that number in context. 10 to the 46th ergs is roughly equivalent to the total energy the Sun will produce over 80,000 years. 80,000 years of solar output, released in 1/5 of a second, from an object 12 miles wide, from 50,000 light-years away. During that initial spike, SGR 1806-20 briefly became the brightest object in the sky outside the solar system, as seen from Earth, if your eyes could detect gamma rays. For a fraction of a second, this magnetar, located on the far side of the galaxy, outshone every star, every galaxy, every quasar visible from Earth. Its luminosity during the peak of the flare was estimated at roughly 10 to the 47 ergs per second, which is about 25 trillion times the luminosity of the Sun. In that instant, this single magnetar was brighter than most entire galaxies. Brighter than some of the most luminous objects in the known universe, all from a dead star smaller than Manhattan. To understand how a giant flare achieves this kind of power, you need to understand what happens in the moments immediately after the crust cracks. Because the crust fracture is just the trigger. The real engine of a giant flare is something physicists call a trapped fireball. When a massive section of the magnetar's crust fractures, the magnetic field lines anchored in that section suddenly snap into a new configuration. This violent rearrangement releases an enormous amount of energy in the form of radiation and superheated plasma, a seething mix of electrons, positrons, and high-energy photons. In a normal explosion, this energy would simply fly outward in all directions and dissipate. But a magnetar isn't normal. Its magnetic field is so unbelievably strong that it can actually trap this fireball. The magnetic field lines form a closed structure above the fractured region of the crust, like an enormous magnetic bottle. The superheated plasma and radiation are confined inside this bottle, unable to escape. The temperature inside the trapped fireball is extraordinary, reaching hundreds of billions of degrees, hotter than the core of a massive star during its final moments of life. The radiation pressure inside is immense. The plasma is trying to expand, trying to fly outward into space, but the magnetic field holds it in place. Energy continues to pour into the fireball from the still rearranging magnetic field below. The fireball grows hotter, denser, more energetic, trapped against the surface of the magnetar by the very force that created it. This confinement is what makes a giant flare so much more powerful than a simple explosion. Instead of the energy dispersing immediately, it accumulates. The fireball builds and intensifies, concentrating an almost inconceivable amount of energy into a relatively compact volume. And then, when the pressure finally exceeds what even a quadrillion Gauss magnetic field can contain, the fireball ruptures. The magnetic bottle breaks open, and all of that accumulated energy is released in a single catastrophic burst. This is the initial spike that instruments detect, the blinding flash of gamma rays that travels outward at the speed of light in every direction. The energy that was trapped and concentrated by the magnetic field is suddenly free, and it announces itself to the universe. But the fireball doesn't fully dissipate in that first spike. A portion of the hot plasma remains trapped by the magnetic field, still confined in the magnetic structure above the surface. This remaining plasma continues to radiate intensely, and as the magnetar rotates, the hotspot sweeps in and out of view from any given direction, producing the pulsating tail of radiation that follows the initial spike. The tail can last for several minutes, and during that time, the magnetar is still pouring out radiation at a staggering rate, far brighter than any single star in the galaxy. The trapped fireball mechanism explains why giant flares are so much more energetic than you might expect from a simple crust fracture. The magnetic field acts as an amplifier, trapping and concentrating energy before releasing it in a focused burst. Without this trapping effect, the energy would dissipate quickly and the flare would be far less intense at large distances. With it, the magnetar becomes a cosmic flashbulb, briefly outshining galaxies. The radiation arrived at Earth as a blast wave of gamma rays and X-rays. Despite having traveled 50,000 light years, a distance so vast that the light from this event began its journey when our ancestors were still living in caves during the last ice age, the radiation was still powerful enough to produce measurable effects on our planet. The first effect was on satellites. The gamma ray flux overwhelmed the detectors on virtually every high-energy astrophysics satellite in orbit. The RHESSI Solar Observatory, which monitors the sun in X-rays and gamma rays, had its detectors saturated. Other spacecraft experienced similar saturation. Some instruments were temporarily blinded, unable to function until the initial spike had passed. For those brief moments, the gamma ray sky was so bright from this single source that nothing else could be measured. The second effect was on Earth's magnetosphere. The magnetosphere is the magnetic bubble generated by Earth's internal magnetic field that surrounds the planet and shields it from the solar wind and cosmic radiation. Under normal conditions, the magnetosphere extends roughly 65,000 kilometers on the sunward side of Earth and stretches far deeper on the night side. The burst of radiation from SGR 1806 -20 physically compressed Earth's magnetosphere. The radiation carried enough energy and momentum that it pushed the magnetic field inward, shrinking the protective bubble around our planet. This compression was brief, lasting only as long as the most intense phase of the flare. But it was real and it was measured. A star 50,000 light-years away physically deformed the magnetic shield surrounding our planet. The third effect was on the ionosphere. The upper layers of Earth's atmosphere, between about 60 and 1,000 kilometers altitude, were ionized by the incoming radiation. The degree of ionization was comparable to what happens during a moderate solar flare, even though this radiation source was not the sun, but a star 50,000 light-years away. The ionospheric disturbance affected radio wave propagation, causing measurable changes in how certain radio frequencies traveled through the atmosphere. Navigation systems and communication systems that rely on ionospheric reflection were briefly affected. Scientists at multiple ground-based observatories recorded the disturbance independently, confirming it was a real atmospheric event rather than an instrument error. Think about what that means. A dead star on the far side of the galaxy, an object you could never see with the naked eye, an object so small and so distant that the most powerful optical telescopes on Earth can barely detect it, reached across 50,000 light-years of empty space and physically altered the atmosphere of our planet. It compressed our magnetic shield. It ionized our upper atmosphere. It blinded our satellites. And it did all of this in a fraction of a second without warning, from a distance so enormous that the light carrying this energy had been traveling since before the last ice age ended. Now, let's talk about what this radiation actually consists of, because the type of energy a magnetar releases is important for understanding why it's so destructive at such vast distances. When a magnetar's crust fractures and the magnetic field rearranges, the energy comes out primarily as gamma rays and hard X-rays. These are the highest energy forms of electromagnetic radiation. Visible light, the kind your eyes detect, has photon energies of about 2 to 3 electron volts. X-rays used in medical imaging have energies of tens of thousands of electron volts. The gamma rays from a magnetar giant flare have energies of hundreds of thousands to millions of electron volts per photon. Each individual photon in this burst carries tens of thousands to hundreds of thousands of times more energy than a photon of visible light. This matters because higher energy photons are more penetrating. Visible light can be blocked by a sheet of paper, by a wall, by the atmosphere. X-rays can penetrate skin and soft tissue, which is why they're useful for medical imaging, but also why radiation exposure is dangerous. Gamma rays can penetrate thick layers of material. They pass through walls, through metal shielding, through the human body. Blocking gamma rays requires dense materials like lead or thick concrete. The gamma rays from a magnetar flare are energetic enough to penetrate deep into planetary atmospheres. Earth's atmosphere is thick enough to absorb most of them before they reach the ground, which is why the December 2004 event didn't cause direct harm to people on the surface. But the absorption process itself is what caused the ionospheric disturbance. The gamma rays were stopped, but in stopping them, they ripped electrons from atmospheric molecules, creating a shell of ionized gas in the upper atmosphere. For a planet with a thinner atmosphere, or for a planet closer to the magnetar, the consequences would be far worse. If the December 2004 flare had originated from a magnetar just a few 50,000 light years away instead of 50,000, the radiation flux at Earth would have been hundreds of times more intense. The ionospheric effects would have been dramatically stronger. At even closer distances, within a few hundred light years, a giant flare could potentially strip a significant portion of a planet's ozone layer, exposing the surface to dangerous levels of ultraviolet radiation from its own sun for years or decades afterward. The ozone layer, that thin shell of molecules in the stratosphere that absorbs most of the sun's harmful ultraviolet radiation, is chemically fragile. High-energy radiation breaks apart the ozone molecules, and it takes time for them to reform. A sufficiently intense burst of gamma rays could catalyze chemical reactions in the stratosphere that destroy ozone faster than natural processes can rebuild it. This is exactly what happens during major solar flares, but on a smaller scale. A magnetar giant flare from a few hundred light years away would be like a solar flare amplified millions of times. The ozone depletion could be severe enough to cause a mass extinction event on any planet with surface life. That depends on ozone protection. And at even closer distances, within about 10 light years, the radiation from a giant flare would be directly lethal. The flux of gamma rays would be intense enough to deliver a fatal radiation dose to any unshielded organism on the surface of a planet. The lethal dose of radiation for a human is roughly 4 to 5 sieverts. At a distance of about 10 light years from SGR 1806-20's giant flare, the radiation dose would exceed this threshold. You would receive a lethal dose of radiation in a fraction of a second. You wouldn't feel it happening. Gamma rays are invisible. They don't produce a flash you can see. They don't make a sound. You would be standing on the surface of your planet, looking up at a perfectly normal sky, and the radiation would pass through your body, shredding DNA, destroying cells, delivering a dose that would kill you within days or weeks. And you would have had no warning. The radiation travels at the speed of light. There's no advanced signal that arrives before it does. The first evidence of the flare is the flare itself, arriving at your planet at the maximum speed the universe allows. Now, consider how this compares to a black hole. Everything we've just described, the flare, the radiation, the atmospheric effects, all of it was delivered across 50,000 light years by an object with a fraction of a black hole's mass. A stellar mass black hole is only lethal within a few hundred miles of its event horizon. Its gravity is devastating at close range, but at the distance of a single light year, it's undetectable and harmless. Even the supermassive black hole at the center of the Milky Way, Sagittarius A star, with its 4 million solar masses, poses no direct physical threat to Earth at our distance of 26,000 light years. It can't reach out and ionize our atmosphere. It can't blind our satellites. It can't compress our magnetosphere. It just exists, massive and patient and passive. A magnetar, by contrast, is a fraction of the mass, occupies a millionth of the volume, and yet produced an event that measurably affected Earth from 50,000 light years away. This is the fundamental asymmetry that makes magnetars more immediately terrifying than black holes. Black holes are more massive. Black holes last longer. Black holes have stronger gravity at close range, but black holes are passive. They influence their surroundings through gravity alone, and gravity falls off with distance. A magnetar is active. It stores colossal energy in its magnetic field and releases that energy in bursts that propagate at the speed of light across interstellar distances, arriving with enough power to affect planets and atmospheres far beyond any black hole's reach. The December 2004 event also revealed something else about magnetar giant flares. The initial gamma-ray spike was followed by a pulsating tail of radiation that lasted several minutes. This tail pulsated with a period of about 7.5 seconds, matching the rotation period of the magnetar. What this means is that after the initial catastrophic fracture, the remaining trapped fireball continued to emit radiation from the magnetic structure above the surface, and as the star rotated, this hot region swept in and out of view like a lighthouse beam. The pulsating tail carried less energy than the initial spike, but was still enormously powerful. During the tail, the magnetar was emitting radiation at a rate of roughly 10 to the 42 ergs per second. That's still 250 million solar luminosities, sustained for several minutes after the main event. The flare didn't just strike once and fade. It continued to pour energy into space for hundreds of seconds, bathing everything within range in a sustained wash of hard radiation. Scientists also detected something remarkable in the tail of the flare: quasi-periodic oscillations, or regular vibrations in the intensity of the radiation, with frequencies that match the predicted seismic vibration modes of a neutron star. The magnetar was ringing like a bell. The starquake that triggered the flare had set the entire star vibrating, and those vibrations modulated the radiation output. By analyzing these oscillations, astrophysicists were able to study the internal structure of the neutron star, essentially doing seismology on an object 50,000 light-years away. The frequencies of the oscillations provided information about the density, elasticity, and composition of the neutron star's crust and interior. It was the first time scientists had been able to probe the internal structure of a neutron star through its vibrations, a landmark achievement in astrophysics. The violence of the event, the sheer destructive power of the flare, also produced some of the most valuable scientific data ever obtained about these objects. Here's something else that underscores just how powerful magnetar giant flares really are. In the years since the December 2004 event, astronomers have realized that some of the short gamma-ray bursts detected from other galaxies, events that were originally classified as a completely different phenomenon, were almost certainly magnetar giant flares seen from extragalactic distances. Gamma-ray bursts, or GRBs, are among the most energetic events in the universe. They come in two varieties. Long gamma-ray bursts, lasting more than 2 seconds, are associated with the deaths of massive stars and the formation of black holes. Short gamma-ray bursts, lasting less than 2 seconds, were traditionally thought to be caused by the merger of two neutron stars. But some short GRBs didn't quite fit the merger model. Their energy profiles, their durations, their spectral properties look slightly different. When astronomers went back and reanalyzed these events with magnetar giant flares in mind, the match was compelling. A magnetar giant flare like the one from SGR 1806-20, if it occurred in a galaxy tens of millions of light years away, would look very much like a short gamma-ray burst to our detectors. The energy output is in the right range, the duration is right, the spectral shape is right. In 2020, researchers confirmed that a short gamma-ray burst detected from the Sculptor galaxy, about 11 million light-years away, was almost certainly a magnetar giant flare rather than a neutron star merger. Additional candidates from other nearby galaxies have been identified as well. Think about what this means. A giant flare from a single magnetar, one dead star 12 miles across, can produce enough radiation to be detected not just across our galaxy, but across intergalactic space. Tens of millions of light years. The flare is so bright that it mimics one of the most energetic categories of events in the entire universe. Astronomers looking at a distant galaxy and seeing a brief flash of gamma rays couldn't even tell the difference between a magnetar flare and the collision of two neutron stars. That's how much energy a magnetar can release. It can impersonate a cosmic catastrophe that involves the destruction of two entire stars simply by cracking its crust. And remember, SGR 1806-20 was 50,000 light years away. If this magnetar had been at the distance of the nearest known magnetar to Earth, which is estimated to be a few thousand light years, the effects would have been catastrophic by comparison. The radiation flux scales with the inverse square of the distance. Cut the distance by a factor of 10, and the flux increases by a factor of 100. Cut it by a factor of 100, and the flux increases by a factor of 10,000. A giant flare identical to the December 2004 event, originating from a magnetar 500 light years from Earth, would deliver roughly 10,000 times as much radiation to our planet. At that intensity, the ionospheric disturbance wouldn't be a minor inconvenience. It would be a severe disruption, potentially damaging the ozone layer and increasing surface ultraviolet exposure for years. At 100 light years, the flux would be 250,000 times greater. The ozone damage would be catastrophic. Surface life would be in genuine danger. At 10 light years, the direct radiation dose could be lethal to unshielded organisms. There are no known magnetars within 100 light years of Earth right now. The nearest confirmed magnetars are thousands of light years away. But magnetars are difficult to detect when they're not actively flaring. And there could be dormant or weakly active magnetars much closer that we haven't identified. The galaxy is estimated to contain tens of millions of dead magnetars, objects that were once active but have since quieted down. Any of these could potentially reactivate if conditions in their interior generate new stress. We simply don't know where all of them are. This is perhaps the most unsettling aspect of magnetar danger. A black hole, at least, is detectable. Its gravity affects nearby objects in ways we can observe. Stars orbit it, gas spirals into it, heating up and emitting radiation. We can find black holes even when we're not looking for them, because their gravitational effects are always present. A magnetar between eruptions is almost invisible. A small, dark, rapidly cooling neutron star, drifting silently through interstellar space. It produces no dramatic gravitational effects. It doesn't pull in gas in spectacular fashion. It might emit faint X-rays from its still warm surface, but at distances of more than a few hundred light years, these emissions are lost in the background noise of the galaxy. You could have a magnetar relatively close to your star system, close enough to threaten your planet during a giant flare, and you would have no way of knowing it was there until the flare happened. And by then, the radiation is already arriving. The 3 confirmed giant flares are almost certainly not the only ones that have occurred in our galaxy during human history. Giant flares from magnetars on the far side of the galaxy, hidden behind the dense gas and dust of the galactic center, could have gone undetected. Flares that happened before the era of space-based gamma-ray observatories, which began in the 1960s, would have been invisible to us. Some researchers have speculated that unexplained ionospheric events or geomagnetic disturbances in Earth's historical record might have been caused by magnetar flares that were never identified as such, because we didn't have the instruments to detect the gamma rays. We might have been hit before without knowing it. This brings us to the core of why the comparison between magnetars and black holes is so striking. A black hole is the universe's ultimate trap. Once you're inside, nothing can save you. But you have to go to it. You have to approach it. From a safe distance, a black hole is just another gravitational source, no more threatening than a star of the same mass. Its danger is local, confined, contained within a sphere that's measured in kilometers or, at most, astronomical units. A magnetar is the universe's ultimate sniper. It sits in the dark, invisible between the stars, storing unimaginable amounts of energy in its magnetic field. And then, without warning, it fires. Not a bullet, but a blast of radiation that travels at the speed of light and can damage atmospheres tens of thousands of light years away. You can't see it coming. You can't hide from it. And you might not even know it exists until the moment it destroys you. That's what makes magnetars, in a very specific and physically grounded sense, more terrifying than black holes. Now we arrive at the question this entire journey has been building toward. Why should a magnetar, a dead star barely 12 miles across, be considered more terrifying than a black hole, the object that most people regard as the most dangerous thing in the universe? To answer that properly, we need to do something that most popular science discussions never bother to do. We need to define what we mean by dangerous. We need to define what we mean by terrifying. Because if you don't define those words carefully, the comparison becomes meaningless. Black holes and magnetars are both extreme objects. They're both born from the deaths of massive stars. They both involve physics pushed to its absolute limits, but they are dangerous in fundamentally different ways. And once you understand that difference, once you see the distinction clearly, the conclusion becomes almost unavoidable. In terms of immediate physical hostility, in terms of what these objects can do to you, and how far away you need to be to feel it, magnetars are worse. Not stronger in every sense, not more powerful in total, but more hostile, more aggressive, more terrifying in the way that actually matters for anything that wants to stay alive. Let's start with the black hole. A stellar mass black hole, the kind formed when a star roughly 25 or more times the mass of the Sun collapses at the end of its life, is defined by one thing above all else: gravity. The core of the dying star collapses past the neutron star stage, past the point where neutron degeneracy pressure can hold it up, and keeps falling. There's nothing left to stop the collapse. The matter compresses to infinite density, at least according to general relativity, forming a singularity, a point of zero volume and infinite density at the center. Surrounding that singularity is the event horizon, the boundary beyond which escape is impossible. For a black hole with 10 times the mass of the Sun, the event horizon has a Schwarzschild radius of about 18.5 miles, making it roughly 37 miles across. Both the event horizon and a magnetar are measured in tens of miles. Both are city-scale objects, born from similar progenitor stars, but with radically different properties and radically different ways of interacting with the universe around them. Now, what happens if you approach a stellar mass black hole? Let's say you're in a spacecraft falling toward it. At large distances, you notice nothing unusual. The black hole's gravity follows the same inverse square law as any other massive object. At the distance of Earth from the Sun, a 10 solar mass black hole would pull on you with a force only 10 times greater than the sun's gravity at that same distance. Significant, but not dramatic. You could orbit it comfortably. Your spacecraft would behave exactly as it would orbiting any 10 solar mass star. The black hole at this range is indistinguishable from a normal star of the same mass. This is a point that surprises most people. Black holes don't suck. They don't reach out and grab things. If you replace the sun with a black hole of the same mass, Earth would continue orbiting exactly as it does now. The orbit wouldn't change. The planet wouldn't spiral inward. The gravitational pull at 93 million miles would be identical. You'd freeze to death because there'd be no sunlight, but you wouldn't be pulled in. As you get closer, things change. Within a few thousand miles of the event horizon, tidal forces become significant. Tidal force is the difference in gravitational pull between the near side and the far side of an object. Because gravity gets stronger as you get closer to the source, the side of your body closest to the black hole is pulled harder than the side farther away. This stretching force increases as you approach. For a stellar mass black hole, the tidal forces become lethal well before you reach the event horizon. Your body would be stretched lengthwise and compressed widthwise, a process astrophysicists call spaghettification. Your feet, if pointed towards the black hole, would be pulled harder than your head. The difference in force would increase until your body was torn apart, stretched into a thin strand of atoms spiraling toward the event horizon. This is genuinely horrifying, but notice the key detail. It only happens when you get close, a few thousand miles at most. Beyond that, the black hole is just a gravitational source, no more threatening than a dark star. Its danger zone is compact. It's measured in thousands of miles, not in light years, not in thousands of light years, in miles. Some stellar mass black holes have accretion disks, swirling disks of gas and dust, spiraling inward toward the event horizon. The most famous example is Cygnus X1, a black hole about 21 times the mass of the Sun that's actively pulling gas from a companion star. As this gas spirals inward, it heats up to millions of degrees, emitting intense X-rays. The radiation from accretion disks can be significant. In extreme cases, the accretion disk around a stellar mass black hole can produce luminosities of tens of thousands of times the sun's output. That's impressive, but the radiation falls off with the square of the distance, just like all radiation. At a distance of a few light years, even the brightest accretion disk around a stellar mass black hole produces negligible radiation. You wouldn't even detect it without specialized instruments. The radiation danger zone of an accreting stellar mass black hole is measured in astronomical units, at most. Certainly not in light years. And many stellar mass black holes aren't actively accreting anything at all. They're just sitting there in empty space, gravitationally inert, producing no radiation whatsoever, completely invisible and completely harmless unless you happen to fly directly into one. Supermassive black holes are different in scale, but not fundamentally different in how they threaten their surroundings. Sagittarius A star, the supermassive black hole at the center of the Milky Way, has a mass of about 4 million times the mass of the Sun. Its event horizon is about 15 million miles across, large enough to fit about 17 of our suns side by side. That's much larger than a stellar mass black hole's event horizon, and the tidal forces near a supermassive black hole are actually weaker at the event horizon than they are near a stellar mass black hole, because the event horizon is so much farther from the singularity. You could actually cross the event horizon of a supermassive black hole without being spaghettified, at least initially. You wouldn't even feel anything unusual at the moment you cross the boundary. It would only be afterward, as you fell deeper, that the tidal forces would grow and eventually destroy you. Sagittarius A star is currently relatively quiet. It's not actively consuming large amounts of matter. It flares occasionally when a cloud of gas wanders too close, but these flares are modest by cosmic standards. At Earth's distance of 26,000 light-years, Sagittarius A star poses zero direct physical threat. Its gravitational influence helps shape the orbit of stars near the galactic center. But at our distance, it's just one of many gravitational influences that determine the overall structure of the galaxy. It cannot reach out and harm us. It cannot send radiation across 26,000 light-years to affect our atmosphere. It just exists, massive and patient and passive. Now, if Sagittarius A star were actively feeding, if it were consuming large amounts of gas like the supermassive black holes that power quasars and active galactic nuclei, the situation would be different. An actively feeding supermassive black hole can produce luminosities that outshine its entire host galaxy. The accretion disk becomes a furnace of radiation, and jets of matter can be launched at nearly the speed of light, extending for thousands of light years. These are genuinely dangerous environments. Stars near the active nucleus can have their atmospheres stripped. Planets can be sterilized by the radiation. But even this danger is concentrated. The radiation falls off with distance. At the distances typical of spiral arm stars like our Sun, the radiation from an active galactic nucleus, while potentially harmful over long timescales, is not the kind of sudden, violent, unpredictable threat that a magnetar poses. An active galactic nucleus is like living downstream of a nuclear power plant. There's a constant, measurable, potentially harmful output. A magnetar is like living next to an uncharted minefield. Everything is perfectly quiet until, without any warning, something explodes. And this is where the comparison comes into sharp focus. Let's line them up side by side. A stellar mass black hole and a magnetar, both formed from dying massive stars, both roughly the same physical size, around 12 to 20 miles across, both incredibly dense. But their threat profiles could not be more different. A stellar mass black hole's danger zone for tidal destruction is a sphere roughly a few thousand miles in radius. Beyond that, it's gravitationally normal. If it has an accretion disk, the radiation danger zone extends to perhaps a few astronomical units. Beyond that, it's undetectable. At 1 light year, it's invisible and harmless. At 10 light years, it might as well not exist. At 1,000 light years, it has literally zero measurable effect on anything. A magnetar's danger zone during a giant flare is measured in tens of thousands of light years. The December 2004 flare from SGR 1806-20 produced measurable effects on Earth from 50,000 light years away. Not theoretical effects. Not effects that required special instruments pushed to their absolute limits. Measurable, real, physical effects. Satellite detectors were saturated. The magnetosphere was compressed. The ionosphere was ionized. From 50,000 light years. As we've already seen, scale that distance down and the effects escalate from atmospheric disruption to ozone destruction to outright lethal radiation doses on the surface. The physics is simple. The inverse square law is merciless. And a black hole at any of those same distances would be doing absolutely nothing. Nothing a stellar mass black hole does can match this. Not at these distances. Not at any distance beyond its immediate gravitational neighborhood. The black hole is more powerful in total gravitational terms, yes. Its gravity is stronger at close range, yes. It can trap light, which a magnetar cannot. It can distort spacetime in ways a magnetar cannot. In these senses, a black hole is the more extreme object. But power and hostility are not the same thing. A nuclear warhead sitting in a bunker is powerful. A person standing outside with a rifle is more immediately hostile. The warhead might contain more total energy, but the person with the rifle can project harm at a distance, unpredictably, without you needing to approach. A magnetar is the rifleman of the cosmos. A black hole is the warhead in the bunker. Let's make this even more concrete. Imagine you're on a planet orbiting a star. You're living your life, going about your business. There's a stellar mass black hole drifting through space, 20 light years from your star system. Should you be worried? No, not even slightly. A stellar mass black hole at 20 light years is gravitationally irrelevant. It's not pulling your planet. It's not emitting radiation. It's not doing anything. It's a gravitational point source lost in the vastness of interstellar space. You would need a dedicated astronomical survey to even know it was there. And even then, you might miss it because isolated black holes are incredibly difficult to detect. Now imagine the same scenario, but instead of a black hole, it's a magnetar. An active magnetar, 20 light years away. Should you be worried? Yes. Absolutely yes. Because you don't know when it will flare. You don't know how powerful the flare will be. And if it produces a giant flare, the kind that SGR 1806-20 produced in 2004, the radiation at your planet, 20 light years away, would be roughly 6 million times more intense than what Earth experienced from 50,000 light years. That's not an inconvenient ionospheric disturbance. That's a potential extinction level event. The ozone layer would be devastated. The surface would be bathed in hard ultraviolet radiation for years. Ecosystems would collapse, complex surface life might not survive, and you would have had no warning. The magnetar might have been quietly sitting there for decades, centuries, producing occasional small bursts too faint to notice at your distance. And then one day, the crust fractures catastrophically. The magnetic field snaps into a new configuration, and a wall of gamma rays traveling at the speed of light arrives at your planet. By definition, you cannot be warned faster than the radiation itself. The information that the flare happened and the destructive energy of the flare travel at exactly the same speed. The messenger and the bullet are the same thing. This is what physicists mean when they talk about immediate hostility. A black hole is dangerous if you approach it. A magnetar is dangerous if it's anywhere near you. The black hole requires you to make a mistake, to wander too close. The magnetar requires nothing of you at all. You can be doing everything right, keeping your distance, minding your own business, orbiting your star in perfect safety. And the magnetar can still reach you. And this isn't just a theoretical concern. There's genuine scientific discussion about whether a magnetar or a similar gamma ray event has already caused mass death on Earth. About 445 million years ago, at the boundary between the Ordovician and Silurian geological periods, Earth experienced one of the most severe mass extinctions in its history. Roughly 85% of all marine species were wiped out. Entire families of organisms that had dominated the oceans for millions of years vanished. Trilobites, brachiopods, graptolites, corals, all of them suffered catastrophic losses. The extinction happened in two distinct pulses. The first pulse coincided with a sudden, severe glaciation, a rapid cooling that locked up enormous amounts of water in ice sheets and dropped sea levels dramatically. The second pulse came when the ice melted and conditions changed again. For decades, the glaciation itself was considered the primary cause, but some researchers have proposed a more dramatic trigger: a gamma-ray burst or a magnetar giant flare striking Earth from a cosmically close distance. The hypothesis, first proposed in detail in 2004 by astrophysicists Adrian Melott and Brian Thomas, goes like this. A burst of gamma radiation from a source within a few thousand light years of Earth could have severely damaged the ozone layer. With the ozone layer stripped away or dramatically thinned, the surface of the Earth, and especially the shallow oceans where most Ordovician life lived, would have been exposed to intense ultraviolet radiation from the sun. This radiation would have killed surface-dwelling organisms directly and disrupted the base of the food chain by killing phytoplankton and other photosynthetic organisms. The chemical reactions triggered by the gamma rays in the upper atmosphere would also have produced large quantities of nitrogen dioxide, a brown gas that would have blocked sunlight and cooled the planet, potentially triggering the glaciation that the geological record shows. In this model, the gamma ray event doesn't just cause direct radiation damage, it triggers a chain of atmospheric and climatic effects that compound the destruction over years and decades. This is still a hypothesis. There is no conclusive proof that a magnetar flare or gamma ray burst caused the Ordovician extinction. The geological evidence is consistent with the idea, but it's also consistent with other explanations. The timing, the pattern of extinction, the evidence of ozone damage in the fossil record, all of it fits, but none of it proves the case beyond doubt. What the hypothesis does show, however, is that the threat from magnetars and similar objects is not purely theoretical. Serious scientists studying Earth's actual geological history have concluded that a gamma-ray event is a plausible explanation for one of the 5 worst mass extinctions our planet has ever experienced. The danger from magnetars isn't something that might happen in some distant, abstract future. It may have already happened. 445 million years ago, life on Earth may have been devastated by a burst of radiation from a dead star that no living thing on the planet could see, detect, or prepare for. But there's an important nuance to the magnetar and black hole comparison that we need to address, because it isn't a simple matter of one being worse than the other in every way. It's more complicated than that, and the complexity is what makes it fascinating. Black holes are permanent, or very nearly permanent. A stellar mass black hole, once formed, will exist for an almost unimaginable length of time. According to Stephen Hawking's theoretical work, black holes slowly evaporate through a process called Hawking radiation, emitting tiny amounts of energy over fantastically long timescales. A stellar mass black hole would take roughly 10 to the 67th years to fully evaporate. That's a 1 followed by 67 zeros. To put that in perspective, the universe is currently about 10 to the 10th years old, roughly 14 billion years. A stellar mass black hole will last for 10 to the 67th years. That's so much longer than the current age of the universe that the comparison is essentially meaningless. For all practical purposes, black holes are eternal. They will outlast stars. They will outlast galaxies. They will be among the last objects remaining in a universe that has gone cold and dark. In the far, far future, trillions upon trillions of years from now, long after the last star has burned out and the last white dwarf has cooled to a frozen cinder, black holes will still be there, slowly evaporating in the dark. A magnetar's active phase, by contrast, lasts about 10,000 years. That's how long the magnetic field remains strong enough to produce the violent flares and bursts that make magnetars so dangerous. After 10,000 years, the field decays. The internal stress diminishes. The crust settles. The magnetar becomes a quiet neutron star, still dense, still spinning, but no longer producing the catastrophic energy releases that define its active life. 10,000 years sounds like a long time by human standards. Civilizations can rise and fall in 10,000 years, but by cosmic standards, it's nothing. It's a flicker. The universe is nearly 14 billion years old. A magnetar's active phase represents less than 1/1,000,000th of that. So here's the nuance. A black hole is a permanent, low-level threat that will exist essentially forever, but is only dangerous at close range. A magnetar is a temporary, extreme threat that can reach across the galaxy, but only for a brief window of cosmic time. The black hole is like a deep pit in the ground that will always be there. The magnetar is like a landmine that's incredibly powerful, but eventually goes inert. Both are dangerous, but they're dangerous in different ways, over different distances, and over different timescales. Which is more terrifying? That depends on what scares you. If what frightens you is permanence, inevitability, the idea that something exists that will outlast everything else in the universe, then black holes win. They are the ultimate patient predators, waiting in the dark for the rest of the universe to come to them, one atom at a time. If what frightens you is immediate destructive reach, the idea that something can kill you from across the galaxy without warning, without giving you any chance to prepare or escape, then magnetars win. They are the universe's most violent outbursts, projecting lethal energy across distances that dwarf anything a black hole can threaten. There's another dimension to this comparison that deserves attention. What happens to your body? And here, magnetars reveal yet another form of hostility that has no parallel with black holes. We've already discussed what happens at a distance, the gamma-ray death from hundreds of light years away. But what about close range? What happens if you could somehow survive the radiation and approach a magnetar to within a few hundred miles? Imagine you're approaching a stellar mass black hole first. As you get close, the tidal forces begin. Your body stretches. It's slow at first, a gentle pulling sensation, but it accelerates. The stretching becomes painful, then agonizing. Then your body simply comes apart. Muscles tear. Bones snap. Your body is drawn out into a thin filament of atoms, falling toward the singularity. The process is grotesque, but it's also, in a strange way, mechanical. It's gravity doing what gravity does. There's a simplicity to it, a physical directness. You're being pulled apart by a force you've known your entire life, just magnified to an unbearable degree. Now imagine approaching a magnetar instead. At a distance of about 1,000 miles, the magnetic field is still in the range of trillions of Gauss. At this strength, the field begins to interact with the water molecules in your body. Water is diamagnetic, meaning it's weakly repelled by magnetic fields. At the field strengths near a magnetar, this interaction is no longer weak. The water in your cells, in your blood, in your tissues, would experience forces strong enough to distort biological structures. But that's just the beginning. As you get closer, within a few hundred miles of the surface, the field reaches hundreds of trillions of Gauss or more. At this strength, the field doesn't just push water around, it fundamentally disrupts molecular chemistry. The electron orbits that form chemical bonds, the bonds that hold every molecule in your body together, are distorted and broken by the magnetic force. The molecules that make up your cells can't maintain their structure. Proteins unfold. DNA strands are pulled apart not by radiation, but by the direct mechanical action of the magnetic field on the electrons that hold the molecule together. Your body doesn't get stretched into a thin strand like it would near a black hole. Instead, the chemistry that makes you a living organism simply stops working. The atoms are still there. The matter is still there. But the molecular structures that organize those atoms into something alive are destroyed. You dissolve at the molecular level. Not because of heat. Not because of radiation. Not because of gravity. Because the magnetic field makes biology physically impossible. This is a form of destruction that has no equivalent anywhere else in the universe. A black hole kills you with gravity. A magnetar at close range kills you with magnetism, by making the chemistry of life impossible. At long range, it kills you with radiation. It has multiple mechanisms of destruction operating at different distances, each one lethal, each one different from the last. A black hole has one trick: gravity. An extraordinarily powerful trick, yes, but just one. A magnetar has at least three: magnetic disruption of matter at close range, radiation death at intermediate distances, and atmospheric and ozone damage at extreme distances across thousands of light years. No other object in the universe has this layered, multi-scale threat profile. Now imagine you're 500 light years from a magnetar when it produces a giant flare. You notice nothing at first. The sky looks normal. The air feels normal. You're standing on the surface of your planet, breathing, thinking, living. And then the gamma rays arrive. They pass through you. They pass through the walls of your home, through the ground beneath your feet, through the atmosphere above you. They interact with the molecules in your body, ionizing atoms, breaking chemical bonds, shredding strands of DNA in every cell. You feel nothing during this process. Gamma rays don't register on human senses. There's no pain, no heat, no light, no sound. The damage is silent and invisible. You go about your day, perhaps for hours, not knowing that the cells in your body are already dying, that your DNA has been torn apart in billions of places, that your bone marrow is failing, that your immune system is collapsing. By the time the symptoms appear, nausea, weakness, bleeding, it's too late. The dose was lethal. You received it in a fraction of a second from an object you couldn't see, powered by a mechanism you didn't know existed, traveling at a speed that made warning impossible. Which death is more terrifying? Spaghettification by a black hole requires you to travel to the black hole. You had to go there. You had to cross thousands of light years of space and deliberately approach the most gravitationally intense object in the universe. In some sense, it's your fault for getting close. Radiation death from a magnetar requires you to do absolutely nothing. You're on your own planet, living your own life, and death arrives at the speed of light from an object you never knew existed. There's something deeply unsettling about that. The black hole kills you because you went to it. The magnetar kills you because it came to you. Let me bring this all together with a final thought on what magnetars represent in the broader context of the universe. Magnetars are rare. Only about 1 in 10 neutron stars becomes one. Their active lifetimes are short, about 10,000 years. At any given moment, there might be only a few dozen active magnetars in the entire Milky Way. The chance of a giant flare happening close enough to Earth to cause serious harm during any given human lifetime is extremely small. We are not in immediate danger from magnetars. The nearest known active magnetars are thousands of light years away, far enough that even a giant flare would produce only minor effects. But magnetars represent something profound about the nature of the universe. They show us that danger in space doesn't always come from the objects we expect. Black holes dominate popular imagination. They're in movies and books and television shows. They're the monster in the closet, the boogeyman of space. And they are genuinely extreme objects, worthy of the awe and fear they inspire. But they are passive. They wait. They rely on things coming to them. Magnetars remind us that the universe is capable of producing objects that actively project destruction across interstellar distances. Objects that combine extreme density with extreme magnetic energy and release that energy in sudden, unpredictable, catastrophic bursts. Objects that can affect planets orbiting stars on the other side of the galaxy. Objects that don't wait for you. Objects that reach out. In our everyday lives, the most dangerous things are rarely the biggest. A mountain is massive, but it sits there. A bullet is tiny, but it moves. The mountain is more powerful in total. The bullet is more immediately hostile. A black hole is the mountain. A magnetar is the bullet. And when you look up at the night sky tonight, at all those quiet, peaceful points of light scattered across the darkness, remember that somewhere among them, hidden in the vast spaces between the stars, there are magnetars, dead stars wrapped in magnetic fields so powerful they distort the vacuum of empty space. Stars that store more energy than the sun will produce in 1,000,000 years, packed into an object the size of a city. Stars that are, right now, building towards the next catastrophic fracture, the next starquake, the next giant flare. Most of them are far away, most of them are dormant, most of them will never affect Earth in any measurable way. But they are out there, silent, invisible, waiting for their crust to crack. And when one does, when the magnetic field snaps, and the energy pours out in a blinding flash of gamma rays traveling at the speed of light, there will be no warning, no advance signal, no time to prepare. The light that tells you the flare happened and the radiation that can damage your atmosphere arrive at exactly the same moment. That is why magnetars are more terrifying than black holes, not because they're more powerful in every sense. They're not. Not because they last longer, they don't. Not because they distort space-time more dramatically. They don't do that either. Magnetars are more terrifying because they are hostile in a way that black holes are not. They don't wait. They don't require you to approach. They project violence across the galaxy at the speed of light, and they do it without warning, without mercy, and without any regard for how far away you think you are. A black hole can be avoided. A magnetar, if it's close enough and active enough, cannot. And in a universe where most of the things that can kill you require you to go to them, something that comes to you is, by any reasonable definition, more terrifying. The universe is vast and mostly empty. Most of it is cold and dark and utterly indifferent to whether you live or die. Black holes sit in that darkness, patient and permanent, dangerous only to those who wander close. Magnetars sit in the same darkness, but they burn. Briefly, violently, magnificently. And when they burn, the fire reaches across the stars. Sleep well tonight. And remember, somewhere out there in the quiet dark between the stars, the crust of a magnetar is slowly cracking,